Hello, everyone. This is Brian Putt. Today, I'd like to talk to you about contingency calculations. What is right, and perhaps some things that can go wrong. So I looked up on Gemini, the AI program, how to calculate contingency. They gave three answers. One was expert judgment. Get an estimate and add 5 to 15% to the project, and that's your contingency. Expert value method. Calculate the cost if something happens, and then multiply that times the probability it happens and add those up. And then the Monte Carlo method, more elaborate, they contend for larger projects. However, I would contend with today's computers and technology that could probably be applied to almost any project. So we're going to look at an example model that has multiple cost categories. Actually, it's got 18 categories, 18 elements. Each has a low, most likely and high value that represents a triangular distribution. This is quite often a way that the cost estimates are put together because subject matter experts can oftentimes relate to those words, okay? And then each is sampled and added together and then run 1,000 trials. You calculate the expected value, and then you calculate the P80 reflecting the budget. And the contingency is whatever your budget is, subtracted from the P80. Now, what is a P80? Let's look at this graph here. What's the P80? The P80 says it's right here, and there's a 20% chance that my cost could be over that amount, and an 80% chance to be less. So if you did it for the P80 with the contingency, you're kind of within your budget with the contingency. So let's review the model. Here is the model. These are my cost categories. It's actually set up as a plant 1 and a plant 2. And then there's a plant 3 that looks different. And then G&A. And they've established a forecast that was based on the mode, or maybe the mode was established first. In any case, it's $90 million. Let's call it $90 million. And these modes or forecasts became the mode over here of this triangular distribution. And then there was a minimum and a maximum estimated. Here are the distributions of each of those. We don't need to look at those triangular distributions right now. So what does all this mean? Well, it comes down to this. This is the total cost. It's 102, and it ranges from, call it 85 to, call that 127 or something of that nature, right? Now, the problem with this is that these variables are all correlated. And I can do that by comparing the maintenance cost to the diesel cost. We wouldn't expect those to be correlated at all. Diesel cost is whatever the diesel costs, and maintenance cost is fixing all your equipment. But you can see they're totally correlated. When the diesel cost is low, so is the maintenance cost. When diesel cost is high, the maintenance cost is high. That's not right. They should be independent. So if I change this model to being independent, uncorrelated, now let's look at that same graph. Here's this graph now. You can see that they're not correlated. It's not a straight line. They're randomly sampled. Sometimes they are high, sometimes they are low, but you know, there's a lot of things in the middle here. And what's the impact of that? Oh, well, now I have a cost of 102 EV, expected value, but my range only goes from about 95 to 110. So now let's compare the correlated and uncorrelated. So here you can see this range. Now, my forecast didn't change. My forecast is still 90.27. But where does that 90.27 fall on this correlated graph? It's down here. It's not even on the curve. What this would suggest, if I'm using the sum of these modes as my forecast, the chance of it really being on, even happening at that level is none, zero, nil. Now, I will admit that to say it's always correlated or totally uncorrelated, those are the bookends. The reality is somewhere in between. Some things are going to be somewhat correlated. And that'll depend upon the project and what the categories are and everything else. So that's something you need to look at separately. So let's come back to this PowerPoint. How should contingency be calculated? What level of risk are you willing to accept? Let's assume 20% chance of going over, i.e. the 80 P80 result. What chance do you want the project team to stay on budget? The 50 percentile would be a P50. Whatever the EV is, call it P50 or P60, that's probably more typical. Aggressive budget would be something low value, like a P20 or a P30. You're really not expecting them to achieve that without some sort of contingency. But remember, the higher the budget, the lower the contingency. Now, in addition to the contingency, some companies will have something called a management reserve. And that typically takes you from the P80 to the P95. And that's kind of kept at the management level. And the project team needs to come back to the management and say, okay, we're going to be over budget. We need some more money to deal with. And they can release some of that management reserve. So I've done this model with SIPmath. And you can visit www.probabilitymanagement.org to learn more about SIPmath. It was developed by the executive director, Sam Savage, and he has a book called The Flaw of Averages and also a new book called ChanceCalc. And if you want to learn some more without spending any money, you can look at my YouTube channel, Brian Putt, that covers all the SIPmath modeling tools, cost and schedule risk analysis, portfolio value of information, and then there's some fun problems there like the birthday problem that's more complete than you're used to doing. And let's make a deal. There's a frog problem and value taxi cab problem. Those are more value of information exercises. They're really simple to think about and can be very thought-provoking, particularly if you have students. Thank you for watching.